Good evening to all. I welcome you all to the 13th online lecture of the course Experimental Methods in Thermal Engineering. In our previous lecture, we started our discussion on the measurement of surface tension, and I have particularly discussed about the methods for measurement of surface tension using force method. In today's this lecture, what we will try to do, first we will try to see the remaining portions of drop shape based methods for measurement of surface tension, and after that we'll start our discussion on contact angle, okay, which is particularly of relevance when we are having three phase contact. Okay, so let us start first with the measurement of surface tension using the method of drop shape. So what we are considering over here, we are considering that we are having a capillary. Okay, so this is a capillary over here, and to this capillary one droplet is actually hanging over here, and this type of droplet is referred to as pendant droplet. Now we have fixed our coordinate system over here, and we have fixed in such a fashion so that the origin of this coordinate system is at the apex of the droplet, and we are having x coordinate in radial direction, and in axial direction we are having z coordinate. Okay, and over here this s nothing but represents the surface of the drop. So now what we have considered that if we take arbitrary any location on our surface, say we are considering uh, surface small elemental surface ds, so that is making an angle alpha with reference to our z axis. Okay, so what we can do if we have to find out the value of pressure at any point over this interface, that pressure we can relate with the Young Laplace equation. So I can write pressure as Pi minus P naught, which will be nothing but equal to Pi minus P naught at Z is equal to 0. So Z is equal to 0 is our this point. So we are considering value of pressure at apex of the drop minus, because at this point we will be having some addition of the gravitational head. So that gravitational head is actually subtracted over here, which is nothing but equal to delta rho times G into Z. Okay. Now, one more picture I have given you over here in order to give the three-dimensional representation. So, in this particular picture, you can see that we can consider our element on our periphery of the droplet. Okay, and in this particular profile over here, what we are having, we have considered one radius over here. So, you can see this is R1. So, this is representing one principal radius of curvature. Okay, so particularly this is taken on a plane, on a particular plane which is actually passing through the z-axis. Okay, and then we have taken another radius of curvature R2 over here. So this particular value is nothing but R2, and this is taken on a plane which is perpendicular to our earlier plane. Okay, so these are R1 and R2 represent over here nothing but two principal radius of curvature. Now, if we fit a circle at the apex, so we will be getting profile something like this. Okay, so this is nothing but the profile circle fitted at the apex. So we are considering that the radius of this circle is nothing but equal to b. Okay, then we have defined that this curvature is actually making some angle phi. So this is not phi actually. If you refer to our previous figure, this is nothing but tending to alpha only. Okay. So if you just apply some geometrical manipulations over here, trigonometric manipulations, you will be finding that the value of 1 by R1 will become, that is nothing but our curvature in one plane, that will be becoming equal to d alpha by dx, and curvature in the another plane R2 will become sine alpha divided by x. Okay. So now what we will be doing, particularly we know that our value of this pressure on the left hand side, Pi minus P naught, I can write this as from our Young Laplace equation as nothing but equal to sigma times 2 into h. So now we are having the individual radius of curvature 1 by R1 and 1 by R2. So particularly the value on the left hand side, I can simply write as sigma LF into d alpha divided by dx plus sine alpha divided by x. So that's what we have done. So whatever we are having over here the pressure on the left hand side, this pressure we are considering at any arbitrary surface location. So this pressure nothing but, because we have measured the curvature of that particular location, so I can write from the Young Laplace equation this as nothing but equal to sigma LF times d alpha by dx plus sin alpha by sin x. Okay, so if we just rearrange the different terms, so we can write keep d alpha by dx on the left hand side, that will be equal to pi minus p naught at z is equal to 0 divided by sigma LF minus delta rho gz divided by sigma LF, and whatever this plus sign alpha by x was there on the left hand side, this we have taken to the right hand side. So it will be coming now as minus sin alpha divided by x. Okay. Now, what we can do, if we try to find out the curvature at the apex of the drop, now at the apex of the drop, profile of drop is almost spherical. So particularly what will be happening, both the radius of curvature we will be finding as nothing but b. Okay, both the principal r1 equal to r2 will be equal to b, and this thing will be applicable only at the apex of the drop. Okay. So because of that, what will be happening? This pi minus p naught at z is equal to 0. I can simply relate it to the value of sigma into curvature, and curvature will become 2 by b. So that's why over here what we have done now, we have written pi minus p naught at z is equal to 0 divided by sigma is equal to 2 by b. Okay. So now if I substitute back this value over here, what I'll be finally getting? I'll be getting d alpha by dx equal to 2 by b minus delta rho g z divided by sigma minus sin alpha by x. Okay. So now over here, if you see in this particular equation, what we are to vary the point along the shape of our droplet or profile of our droplet, value of alpha will be changing. So alpha is a variable, and then at each and every surface profile, we will be having different value of x and z coordinate also. Okay, so for example, over here, if I consider my coordinates as x comma z, at another point it may be some point x1 z1, and at another location it may be some another point x2 z2. Okay, so it means in this single equation now we are having three variables. We are having one alpha variable, then we are having another variable as z, and then we are having another variable as x. Okay. So it means we cannot find out the value of all these three variables from this single equation. So what we have to do now, now we require two more additional equations. So what we will be doing for finding out the two more additional equations, we will be considering that this is my surface S. Okay. Now if I consider that this particular angle is nothing but alpha, and if I take a small angle over here as nothing but equal to d alpha, and this small distance whatever I have taken over here, small elemental surface, this I can write it as ds. Okay. So particularly you can see over here, initially we were having some value of x as x1, and then we are having some another value of x as x2. So change of x over here is nothing but equal to x1 minus x2. Now if you relate that one with this small value of d alpha, and if you apply the trigonometry, you will be simply finding over here that dx is nothing but equal to cos alpha times ds, and dz, so dx is clear. So this point is actually what I have written as x2 minus x1. This point represents dx, and dz will be, this is my one location and this is my another location. So this particular distance is nothing but equal to dz. So if you apply over here trigonometry, you will be finding that dx is equal to cos alpha into ds, and dz is equal to sin alpha times ds. So now what we are having, you can see over here that we are having now three equations. One is for alpha, where alpha is actually varying with z and x, and then we are having the one separate equation for dx and separate equation for dz. So these are nothing but for the elemental surface of the drop. So we have taken ds as small elemental surface of the drop. Now if we have to find out the profile from this elemental surface for the entire pendant drop, what we have to do, we have to apply over here integration. So what we can do on these three different equations, now we can apply over here numerical integration. Okay, so we can apply over here numerical integration. So when we will be doing the numerical integration, now we require, because we are having three different equations, and if you see the order of each equation is nothing but unity. So order of this equation is also 1, d alpha by dx. Over here it will be dx by ds, order is 1, and dz by ds, here also order is 1. So if we are having three equations of single order, while we will be performing the numerical integration to find out the entire step of the drop profile, in that case what we have to do, we require three boundary conditions. Okay, so the very first boundary condition will be when we are having x equal to 0, at that time what will be happening, value of, so here you can see, when we are having x equal to 0, at that particular time we will be having value of surface also equal to 0. Similarly, when z is 0, then also our s will be equal to 0. Okay, and another boundary condition we can write in terms of the elemental surface s. So what will be happening when value of s will be approaching to 0, in that case our value of angle alpha will also be equal to 0. Okay, so if we apply all these boundary conditions over here, what we can do, we can numerically integrate these simultaneously, all these three equations, and finally, because delta rho is known, g is known, so from the integration we will be finding these values of d alpha by dx, dx by ds, and dz by ds. So once we are finding these values, we can determine the value of sigma. Okay, so that is something, while actually the codes or algorithms are developed for determining the surface tension using the drop shape method. Now experimentally, how this procedure is actually employed for finding out the surface tension, let me demonstrate over here. So what will be happening over here, in this particular equation, so you can see this is our main governing equation. Okay, so in this particular equation now, if I consider b, which I have defined as nothing but my radius b as nothing but equal to r naught, and if I rearrange this equation little bit, ultimately I'll be finding over here one beta factor with z. Okay, so that beta factor with z particularly is known as shape factor of the drop. Okay, so how this will be coming, I have just told you the procedure. What you have to do over here, now you have to consider b is equal to r naught, and you have to multiply on both sides by uh, r naught over here. So if you will be doing so, you will be finding over here one term, delta rho g into r naught square divided by sigma. So the coefficient of this z entire term is particularly called as beta, and that beta is something which is known as shape factor. So what we have done over here, delta rho g into r naught. So this r naught is actually something which is equivalent to b, and below there is one term gamma. So gamma is nothing but equivalent to sigma LF. So that is nothing but surface tension of the liquid. Okay. Now it means from here, this tells us that if we know somehow the value of this shape factor beta, we can actually determine the value of gamma, which is nothing but our surface tension of the liquid. Okay. So what generally we do experimentally, we can consider this particular photograph. So in this photograph, you can see from a capillary, a pendant drop is hanging over here. So in this drop, what we have done, first we have found the largest diameter of this droplet. So you can see over here, this particular diameter, which is represented by DE over here, this nothing but represents the largest diameter of the drop. And then what we are having, we have also fitted a circle at the apex, which is giving us this radius r naught. And obviously, what will be happening over here, this r naught will be equal to nothing but dE divided by 2. Okay, now if we move in the axial direction at a distance of DE from the apex of the drop, and if it measures some another diameter which is particularly specified as DS. Okay, so this another diameter we will be getting as nothing but DS. So what we can do, we are having now one empirical correlation available, which tells or which gives the relationship in between beta and DS and DE. So from this relation you can see that if you know from the geometry of the pendant drop, if you know the value of DS and DE, you can use these values to find out the value of this beta, and if you substitute other properties such as density is known, you can determine the value of surface tension. Okay, so this is one experimental photograph. So in this experimental photograph, if you have to find out the shape or value of the R naught, so what is normally done, we go for image analysis using MATLAB also you can do, or you can employ any other software also. Okay, and using the image analysis, what we will do, we will try to initially fit a curve which will be passing through the apex of the droplet. So this is a circle which is fitted over here. Now you can see these points represents the large number of points which are used to fit the circular profile. Okay, now how to determine that what should be the optimum number of points we should use? So for that, what is done over here, you can see by using the number of points on the experimental periphery or experimental picture, a circle has been fitted and its radius R naught is determined. And you can see over here, this R naught is plotted as function of number of points. So you can see when you are having very less number of points, during that point you are having large variations in the value of R naught. And once you are reaching to the sufficient number of points, after that your radius is becoming almost constant irrespective of the number of points you are increasing to fit the curve. Okay, so depending upon that, what you can do, you can determine the optimum number of points what are required to fit this curve. So once you have fitted this curve, you will be getting the value of R naught, and as I have told you that R naught is nothing but DE by 2. So from here you will be getting the value of DE also, which will be particularly representing the maximum horizontal span of this droplet. And once you are knowing the value of DE, then you can move DE times in the axial direction, and you can measure another diameter DS of the pendant drop. Okay, so this particular DS and DE are related to find out the shape factor, and one shape factor of the pendant drop is known. From that we can determine the value of surface tension. Okay, so this is how experimentally it is employed for finding out the surface tension. Okay. Then there is one more method which is known as rotating cylinder method. So in this particular method, what we do, we consider the size of this cylinder of the order of capillary length scale. So we consider it as nothing but some very small cylindrical capillary. And in this particular capillary, we first fill our liquid, and then inside that liquid, normally at the center of the capillary, one small bubble of air is actually injected. Okay, after that what is done, this capillary is subjected to the angular rotation. So because of the angular rotation, what will be happening, there will be some centrifugal force which will be developing inside the fluid, and because of that centrifugal force, what will be happening, whatever the bubble we are having which is encapsulated inside our liquid, that bubble will be actually elongating along the axial direction, and it will be compressing in the radial direction. Okay, so what we have to do over here, we have to consider actually one important point. We have to consider over here transparent capillary. Why transparent capillary? Because ultimately whatever the shape this particular bubble is taking, we have to determine its dimensions. Okay, so generally what we do, bubble will be actually elongating in the axial direction and will be compressing in the radial direction. Okay, so what we do, we consider this bubble equivalent to that of some cylinder, and we consider that that cylinder is having the dimension equivalent to that of RB. Okay, so now if we consider this elongated bubble as nothing but identical to that of a cylindrical profile, and if we minimize the kinetic energies and the surface energies, we will be finally finding that our surface tension is nothing but related to the rotation of the capillary omega square into delta rho into RB cube divided by 4. So this is the relationship in between the value of the surface tension, rotation of the capillary, and radius of this elongated bubble profile when we have considered it identical to that of a cylindrical nature. Okay. In this particular method, what we have to do, we use many times stroboscopic light in order to find out the size of this bubble. So basically, or otherwise we may also have to go for high speed photography, and we have to meet our photography frame rate as per the rotation of the cylinder in order to determine the size of this bubble, elongated bubble. Okay. So one important point you can see over here, that our value of surface tension is nothing but proportional to the square of the angular rotational speed of the capillary. Okay, so what happens if we go for very high angular velocities? In that case, what will be happening? We will be having some unstabilized vibrations in our capillary. Okay, so because of that, particularly this method is preferred for measurement of surface tension of fluids, of liquids which are having actually low value of surface tension. Okay, so particularly this method is applicable for low surface tension, because if we are going for measurement of high surface tension, as it is directly related to the square of the angular velocity, so we will be having very large angular velocities at which it will be difficult to stabilize the capillary. Okay. Then we are having another method, which is a very simple method for measurement of the maximum, for measurement of the surface tension, and this particular method is actually called as maximum bubble pressure method. Okay, so what we do in this method, we are having some capillary, and at the top end of the capillary, we use some device in order to add the fluid over here. Okay, so while this fluid will be coming out of the capillary, initially you can see at point A, so this first profile is actually corresponding to A. So at that point you can see that the radius of curvature is actually very large. So if I plot the radius of curvature with the volume of the bubble which is coming out of this capillary, you will be finding that initially you are having very large radius of the bubble, and slowly this radius of the bubble will keep on decreasing, and then once this radius becomes, or I can say particularly you can see this profile number C. So at profile number C, nothing but our this profile of the bubble is identical to that of a spherical profile. So over here you can see this bubble profile is nothing but identical to that of the spherical profile. So corresponding to that, what will be happening? You will be finding the minimum radius of curvature, and that minimum radius of curvature will be nothing but equal to the radius of the capillary. Okay, so we will be finding one minimum radius of curvature, and value of that minimum radius of curvature will be nothing but equivalent to over here I can call it as RC, radius of capillary. Okay, and when our size of the bubble will be going beyond the entire spherical profile, once again what will be happening, our radius of curvature will be actually increasing. So you can see that this is the profile of the radius of curvature. So it means if you plot curvature, which is nothing but opposite to that of the profile of the radius of curvature. Okay, so from this variation of radius of curvature, we can see that our curvature is getting maximum value when our radius is equivalent to that of the radius of the capillary. Okay, so particularly we can see the maximum value of curvature is nothing but equal to 1 by RC. So 1 by RC in another direction, and 1 by RC will be there in the another direction because of the hemispherical nature. Okay, so due to this, what will be happening? We know that nothing but our pressure drop is proportional to, or pressure drop is equal to sigma times curvature. Okay, so because of that, what will be happening? Because pressure drop is nothing but directly proportional to the curvature. So it means when we will be having the maximum curvature, at that time we will be having the maximum value of the pressure. Okay, and so we can simply say that our delta P max will be equal to nothing but sigma times 2 divided by RC, where RC is nothing but the radius of the capillary. So from here you can determine the value of sigma as delta P max into RC divided by 2. Okay, so one important point you have to do over here, while we will be injecting the fluid over here, gaseous phase over here, what we will be doing, we will be having certain pressure transducer which will be continuously monitoring the pressure of the bubble. Okay, and what will be happening, we will be actually plotting the pressure profile, and whatever the maximum value of pressure we will be getting, corresponding to that we will be considering the radius of curvature as equal to that of RC, and we will be finding the value of surface tension. Okay, so this is a very simple method for determining the value of the surface tension. So earlier it was not popular due to the high cost associated with the pressure transducers, but as the transducers has evolved and now we are having the measurement of pressure possible with low cost transducers also, so now this method has also become actually popular. Okay, so this is all about methods for measuring the value of surface tension. Now let us try to see that if we have to relate the surface tension of any fluid with the help of another thermodynamic properties, then how we can specify. So for that, one relation is available for, over here, which tells that surface tension is nothing but equal to critical pressure to power 2 by 3, critical temperature 2 by 3. Then we are having Q as some value which is specified over here, and multiplied by 1 minus T by Tc. So T is nothing but the temperature at which we are measuring the value of surface tension, and Tc once again refers to the critical temperature. Okay, and value of Q is given over here. So you can see in this particular value of Q, we are having one of the temperature as Tb. So this Tb is nothing but equal to boiling point of that liquid for which we want to measure the surface tension at 1 atmospheric pressure. Okay, so if we apply this relation from here, we can get the value of surface tension. However, it will not be very accurate, but it will be approximately close to the exact value of the surface tension. Okay. Now let us try to see another type of situation. So as I have told you earlier also, that when we are having a droplet which is resting on the surface of solid, that particular type of droplet is actually referred to as sessile droplet. Okay, and normally what will be happening when we are three-phase contact line. Okay, so over here you can see that we are having a solid, then we are having liquid, and outside we are having some fluid. So at that particular point, what is happening, you can see this is a nothing but two-dimensional view. So in this two-dimensional view, at this particular point, you can see we are having the occurrence of both all three phases. A contact point, but in actual practice we will be having some three-dimensional liquid droplet. So because of the three-dimensional nature of the liquid droplet, we will be having existence of a contact line. Okay, so this is nothing but you can see one central plane of that three-dimensional photograph. Okay, so over here there comes one very important concept which is referred to as contact angle. Okay, so what is contact angle? It is nothing but if we take the tangent to the liquid fluid interface, okay, and if we take a tangent to the solid liquid interface, and particularly these tangents we have to take at nothing but our contact line. So we are taking these tangents at nothing but our contact line. So at that time, if we measure the angle in between these two contacts, in these two tangents, and particularly this angle if we measure from the liquid side. Okay, so here also you have to see that we may have angle, we can measure the angle from this side also, because here also this tangent will be extending. So we can measure angle from this side also, or we can measure angle from this side also. So you have to remember that we have to always measure the angle from the liquid side. So if we measure the angle from the liquid side, so whatever this value of theta I'll be getting, that particular value of theta is something which is known as a contact angle. Okay. Now, what happens if we consider that our droplet is resting on an ideal solid surface? In that case, we say that our contact angle is nothing but a ideal contact angle. Okay. So, what are the characteristics of ideal solid surface? Ideal solid surface is nothing but characteristics of ideal solid surface. Okay, it should also be insoluble and non-reactive, means it should not react with the surrounding liquid and fluid, and it should also not be soluble in the fluid and the liquid. Okay, so all these are the characteristics of ideal solid surface. So if we are having the ideal solid surface, particularly for this type of configuration, we are having one famous equation which is given by Young in 1805, and this particular equation is known as Young's equation, which relates the contact angle with the different surface tension values. Okay, so over here you can see, because we are having the three-phase contact, so we will be having particularly over here in this direction as nothing but surface tension in between solid and liquid. Over here we will be having surface tension in between liquid and fluid, and in this particular direction we will be having surface tension in between the solid and the fluid. Okay, so these three surface tensions are actually related by one equation, and this equation is actually relating these three different values of surface tensions with the contact angle. Okay, so over here you will be finding that nothing but this cos theta y is equal to sigma sf minus sigma SL divided by sigma LF. Okay, so that is something which you can see over here is coming from the simple force balance. Okay, so over here what you can do, you can consider net force over here, which will be nothing but sigma SF equal to sigma SL plus sigma LF cos theta. So from there you will be getting the value of cos theta y as equal to sigma SF minus sigma SL divided by sigma SL. So this particular angle cos theta y is something which is known as equilibrium contact angle. Okay. So why it is known as equilibrium contact angle? Because this Young-Laplace equation will be only applicable when our droplet is actually resting on the surface. So this droplet should not have any type of motion. Okay, so that's it is only applicable when droplet is actually in equilibrium with the surface. It has settled over the surface. Okay, so that's why this angle measured from this equation is also known as equilibrium contact angle. Okay. Now, this relationship depends only on the chemical nature of the three phases. So you can see over here what we are doing. We are considering that it is depending upon the value of surface tension between the solid fluid, solid liquid, and liquid fluid. So it means it is only depending upon the chemical nature of the three phases and is independent of the gravity. Okay, so this is one important point, because what will be happening when we will be changing the size of the droplet, then because of the gravitational field there will be distortions in the shape of the drop. Okay, so let me just give you one example. If I take a solid surface which is nothing but of same type of surface, but if I place a small droplet, so that may be of this shape. Then if I place now slightly bigger droplet, that may flatten more over the surface. Okay, and if I take another droplet which is very big, that may even show very huge distortion over the surface. Okay, so you can see over here when we are actually increasing the volume, then because of the gravity there is distortion in the shape of the droplet. But we are saying that whatever this relationship we are having, that is only depending upon the chemical nature of the phases and is independent of gravity. Why? Because if we see over here macroscopically, the profile of the droplet may change, but when we will be looking particularly at the contact point, we will be finding that microscopically nothing but the direction of the tangent or our tangent will be tending in the same direction. Okay, so what is basically happening, because we are not changing the surface characteristics, so whatever the distortion in the shape of the drop is happening, that distortion is only happening because of the gravitational field, so which can be observed macroscopically. But if we see from the microscopic point of view, we can find that particularly at the contact point, there is no change in the profile of the droplet. So because of that, we will be finding that the value of contact angle will be independent of the gravity. Okay. Then whatever the Young contact angle we are having, it represents the state of the drop having minimal Gibbs energy. So means this is nothing but we are calling that droplet is in equilibrium. So it means droplet has actually minimized its surface energy. So it has reached to a state of minimum energy, then only in equilibrium with its surroundings, and corresponding to that, whatever angle we are measuring, that we are measuring from the Young equation. So that's why Young contact angle also represents the minimal Gibbs energy state. Okay. And now if we plot this Gibbs energy versus contact angle curve for an ideal solid surface, we'll be finding that we'll be only having single minima point. So nothing but I am calling it as, like if I plot Gibbs energy delta G as function of theta y, where theta y represents the Young's contact angle, or initially I can call it as theta, any contact angle. So we'll be finding, for if we are having a ideal solid surface, for that ideal solid surface, our nature of the curve will be something like this, and we will be having only a single minima point, and the single minima of energy will be corresponding to nothing but our Young's contact angle theta y. Okay. So that is the case, that if we are having an ideal solid surface, we will be only having a single minimal point at which our Gibbs energy will be minimal. Okay, now what we are having, Gibbs has also suggested that whatever the three-phase mutual interactions we are having, that can be also accounted for by line tension. Okay, so why we are introducing the concept of line tension? Why? What will be happening when there is a perfectly smooth surface? There are chances that at molecular level, this perfectly smooth surface will be actually interacting with the molecules of the fluid and molecules of the liquid. Okay, so these molecular activities or molecular interactions may lead to change in the value of contact angle. So that's why Gibbs has suggested an additional term. That additional term is particularly known as line tension, in order to correct the value of contact angle. Okay. However, later on, after Gibbs has proposed this idea, it has been found that when the length scale of the droplet is less than 1 micron, then only this type of molecular activity become prominent, and the requirement of line tension is there. Okay. So because of that, what has happened, because when we talk about on the engineering length scale, in our engineering length scale, all the droplets are of nothing but millimeter sized diameter, which is far greater than the micron sized droplet. So that's why this particular type of line tension need not to be included for our engineering applications. Okay. Then what we are having now, so you have seen from the previous slide that nothing but cos theta y is related to sigma sf minus sigma sl divided by sigma lf. Okay. So one important point we have to see over here. So now we are having a single equation, and in this single equation, only this value sigma LF value is actually known from our earlier knowledge of measurement of surface tension, whereas we are not knowing the value of sigma SF and sigma SL. And at the same point of time, we also want to measure the value of theta Y. Okay. So generally what is done, we now will take one assumption that whatever the fluid we will be having outside fluid, always if we are having outside fluid in nothing but our gaseous phase. Okay. So if outside fluid is always a gaseous phase, In that case, what will be happening? The value of this surface tension of fluid can be taken as equal to 0. Okay. So one assumption we are taking now, we are considering that our outside fluid is nothing but a gaseous phase, and the surface tension value of this gaseous phase is equal to 0. Okay. And another thing what we will be doing, this sigma SL over here, this is nothing but our interfacial tension. Okay. Why interfacial tension? Because it is the uh, interactive force or adhesion force between the solid and the liquid molecules. Okay, so that's why it is nothing but our interfacial tension. Now already we know that if we are having a two fluid combination, for example, one we are having over here this sigma S and one we are having as sigma L. So for the solid, if I know the value of surface tension of this solid as sigma S and value of the surface tension of this liquid as sigma L, then by using these two values, I can relate the value of this sigma L using our earlier knowledge from the previous lecture. Okay, how we can relate it with the help of adhesion energy. Okay, so if you recall, we were having one coefficient phi, which was nothing but equal to square root of uh, sigma A divided by sigma A. We were taking dispersive part divided by sigma A into sigma B dispersive part divided by sigma B, and we were having phi equal to 2 times of square root of this value. Okay, so if we apply this formulation for finding out the value of sigma L, and we consider over here that this sigma F is nothing but equal to 0, in that case what will be happening? Finally we will be getting one modification of the Young's equation, and we will be finding cos theta y equal to -1 plus 2 times phi square root of sigma S by sigma L. Here, this sigma L is nothing but surface tension of the liquid, and sigma S is surface tension of the solid surface. Okay. Now, let us consider for few example cases that our value of phi is equal to 1. Okay, so for few cases, if we consider that value of phi is equal to 1, and say our values of surface tension are given over here, so in this particular table, so you can see in example 1, sigma L is 73, sigma S is 22. Now if you calculate using this equation by considering value of phi as 1, you will be finding that value of theta for first case is nothing but coming out to be 84.4 degrees. For second case, if you calculate, your value of sigma is coming out to be value of angle is coming out to be 0. And for third case, if you see, our cos theta y is becoming 3.68, which is mathematically not possible, but still we have assigned this value of 0 over here. So why this is assigned, I'll just explain you. Okay. So in the first example, what we are having the value of contact angle as 84.4 degree. And in case of second example, we are having the value of contact angle as 0 degree. Okay. So 0 degree contact angle is usually termed as condition of complete wetting. Okay. So particularly what will be happening in this case, if we are having a droplet which is becoming like a spreading like a thin film over the surface. Okay, so over this entire solid surface, we will be having a very thin film of liquid. So whatever the liquid we will be having, that entire liquid will be spreading over the surface, and it will be completely wetting the solid surface. So that's why this particular situation, when we are having zero contact angle, is referred to as complete wetting. Okay. Then we have another situation. If our contact angle is less than 90 degree, then this particular situation is referred to as partial wetting. Okay, so because in contact angle less than 90, what will be happening? Less than 90 and greater than 0. Okay, because obviously at 0 we will be having complete wetting, and at angle less than 90 we will be having the partial wetting of the surface. Okay, because entire solid surface drop will not spread over the entire solid surface. It will be actually making certain angle with the surface. So in that case, we will be having the condition of partial wetting, as we can see from this figure also. Okay. Then if you see over here in this third case, what we are getting, we are getting the value of cos theta y, which is actually mathematically not possible. Okay, but still we are assigning the value of contact angle to this as equal to 0. So if we are having this type of situation, this situation physically refers to a situation where we are not getting any minima in our free surface energy of the system within the mathematical possible range of the cos theta. Okay, so in that case, what will be happening? Cos theta will be having the minimum value at the boundary angles only. In case if its value is becoming positive, then we will be having boundary angle corresponding to 0 degree, and in case its value is becoming negative, in that case we will be having boundary angle as nothing but equal to 180 degrees. So in case of 180 degree, what will be happening? Our entire droplet will be of actually spherical nature. Okay, and only a single point will be touching the surface. Okay, so if droplet is of spherical nature and a single point is touching the surface, so you can see over here that you are having some point contact. In that case, you will be finding that this is our solid liquid interface and this is our liquid gas interface. So we will be having contact angle of 180 degrees. Okay. Then now what we are having, when we are having a clean solid surface and it is exposed to either air or to any liquid, then it will be actually absorbing some components of the air, and in that case always what happens, effective surface tension will be lower in comparison to the surface tension of a clean solid surface. It means that for a particular solid surface, if value of surface tension was supposed to be sigma x, sigma s, so now the when it is exposed to air, value of surface tension will be less than sigma s. Okay, why? Because ideal clean surface is something which is a very idealized concept, and in reality, when we will be having the interaction of solid surface with surrounding either liquid or air, there will be some molecular activity close to the surface, which will be actually reducing the surface tension of the solid. Okay, so because of that, what will be happening if we consider a system for which theoretically complete wetting is actually expected? Okay, so theoretically we were considering that if sigma L is equal to sigma S, in that case we will be having the complete wetting of the surface. But when in practical situation this type of surface will be actually interacting with the surrounding fluids, there will be decrease in value of sigma. So because of this decrease in value of sigma, instead of complete wetting, we will be finding that we will be having the occurrence of partial wetting. So because of this, particularly this type of surfaces which exchanges, which are having some molecular interactions with the surroundings, which decreases their surface tension, this particular type of surfaces are known as autophobic surfaces. Okay. Okay, so still what we have done, we have seen the different situations, but it is still not clear that how to determine the value of the surface tension of the solid, because surface tension of the solid is something which is not, we have not studied any method yet to find out the surface tension. So in this particular equation, now you can see if we consider that even value of phi is also known, we are having two unknowns, contact angle and sigma. Okay. So how to determine, let us now try to see. So what we are doing over here, now in this particular equation, what we have done, nothing but you can see that earlier I have assumed the value of phi as 1. Okay, but in actual practice, we cannot include the value of phi as 1 because for different type of fluids, its value will be varying. Okay, so what we have done now, from our earlier lecture, we have employed over here the formulation of phi and we have rearranged this equation. So if we rearrange this equation, we will be finding 1 plus cos theta y into sigma L is nothing but equal to phi. So for phi, what we are considering 2 times of square root of sigma S d sigma L d. So this is nothing but representing the dispersive component, okay, of the surface tension, and we have neglected the surrounding fluid which is air. So it means now only the fluids which are in contact, one is solid and one is liquid we are having, drop liquid. Okay, so that's why the value of phi is actually determined using this combination. So when we are considering the surface tension of the solid and surface tension of the liquid. And apart from that, so this is one typo over here. This should be actually P. P is nothing but polar component of the surface tension of the solid and surface tension of the liquid. Okay. So in this particular situation, you can see over here that if we even determine the value of this contact angle theta y from the geometry. Geometry means if we take the experimental snapshot, and from that experimental snapshot, if we try to find out the value of this contact angle theta, equilibrium contact angle theta, in that case also what will be happening, in this particular equation we are having now nothing but two unknowns. One is sigma s dispersive component and another is the polar component of the surface tension. Okay, so that's why in this particular equation, because of the two unknowns, once again when we have related or substituted the value of phi, we are getting a single equation, and there also we are considering that from the geometry we will be finding the value of contact angle. Still we are having actually two unknowns over here. So that's why what we do normally, if we have to find out the value of surface tension of the solid, we will be actually considering two liquids. Okay, two liquids of known surface tension. So I'll be taking sigma L1 and sigma L2 as two liquids in our experiment. Okay, so for first liquid, we will be having this equation. So once again, there is a typo. This should be actually P polar component. Here also it should be P. So nothing but now what will be happening? We are having now, and these particular values of surface tension of liquid 1 and liquid 2 are known. So now what we are having two equations and two unknown. So by employing this formulation, what we can do, we can determine the value of surface tension of the solid, dispersive part as well as the polar part of the surface tension. Okay, so while we select these two liquids over here, many of the times we consider the situation that one of the liquid is nothing but non-polar. Okay, and obviously both the liquids should be dissimilar. We should as much dissimilar as possible. Okay, so that is actually required for the accurate measurement of the surface tension of the solid. Okay, then so till this point, whatever we have discussed, that is actually all about the ideal surfaces when we are having actually clean solid surface. But in actual practice, what will be happening, we will not be having the perfectly smooth surface, and there will be some surface roughness associated with the uh, solid surface. Okay, so because of that, we will be having the formation of two types of contact angles: actual contact angle and apparent contact angle. So actual contact angle, you can see over here, when we take the actual tangent in between the solid and the liquid, and that if we plot with the tangent which is passing through the liquid and the fluid interface, and if we measure the value of angle in between these particular two tangents, that is something which is referred to as actual contact angle. And what we will be doing when we will be doing the experimentation at the macroscopic scale, because particularly the order of this surface roughness will be nothing but in the order of microns. So because of that, what will be happening when we will be doing our experiments over the engineering scale, we will not be able to determine this small roughness values. Rather, we will be considering this surface as nothing but a flat surface. Okay, so for that case, we define some nominal solid surface. So what we will be having, we will be having some nominal solid surface over here. So if we measure the angle in between the nominal solid surface and our liquid fluid tangent, whatever that angle will be appearing to us, that is something which is known as a apparent contact angle. Okay. However, if we go into our actual calculations from the Young-Laplace equation, and if we try to find out the value of contact angle by knowing whatever the angle we will be getting from Young's equation theta y, that will be nothing but equal to that of our actual contact angle. Okay, so it means one important conclusion we are having over here, that if we have to do the numerical simulations, then instead of supplying the apparent contact angle as a boundary condition, we should supply actual contact angle as a boundary condition. Okay, or whatever the theoretical analysis or numerical simulations we are performing, for that we should know about the value of the actual contact angle. Okay, so what we are having certain methods which are developed in the past for determining the value of actual contact angle. That we will try to see in the further slides. One important point I would like to highlight over here, that initially Gibbs has given the hypothesis that what we will be having, if we are having a perfectly smooth surface, we will be having only one point corresponding to the minimum surface energy state. Okay, and if you go for the real surfaces, what you will be finding that if we repeat the experiment multiple number of times, without changing the type of the liquid and the experimental conditions, what we will be having, instead of getting a single value of the contact angle, we will be having multiple values of apparent contact angles. Okay, so we will be finding multiple values of a range of contact angles. So it means, it clearly gives us some idea that when we are having a rough surface, we are not having the occurrence of single minimum stage of Gibbs energy. Rather, we are having multiple stages of minimum Gibbs energy. Okay, so we are having multiple points at which minimal energy state is actually existing. Okay, so now what will be happening when we will be measuring the contact angle for real surfaces, as I have told you that instead of having a single value, we will be having the range of spectrum of values over here. Okay, so how that spectrum of contact angles can be related to find out the actual value of the apparent contact angle or average value of the apparent contact angle, let us try to see that one. Okay, so but before that, what we will try to do, we will try to study one more concept which is known as contact angle hysteresis. Okay, so what is basically contact angle hysteresis? When a drop volume is increased, the contact line appears to be pinned while the contact angle increases. So what we actually trying to say over here, you can see that this is some initial drop profile which is resting over a solid surface. Okay, now what we have done, we have actually increased its volume. So when we have increased the volume, drop has not actually increased its horizontal span. Rather, its contact line has remained sticked to the surface and its shape has actually changed. And when he further increased the volume, its shape has actually further increased. So you can see over here, because of that, what will be happening? Initially, we will be having tangent something like this, then we will be having tangent something like this, and then we will be having tangent something like this. So it means ultimately, when we are increasing the volume of the droplet, our value of contact angle is actually increasing. Okay, so that is what we are trying to say over here, that when the droplet volume is increased, contact line appears to be pinned. So contact line will be actually sticking to the solid surface and its contact angle value will be increasing. Okay, now the apparent contact angle, what will be happening while we are further keep on increasing the volume, there will be increase of contact. If I plot volume versus contact angle, apparent contact angle, there will be increase of contact angle, and at a point it will be reaching maximum, and then once again there will be fall of the contact angle. Okay, so the apparent contact angle eventually reaches a maximum value. Okay, and particularly this maximum value of the contact angle is something which is termed as advancing contact angle. So why we call it as advancing contact angle? Because after achieving this maximum value of contact angle, our droplet will be advancing in the outer direction. So its contact line will be actually moving in the radial outward direction. Okay, so that will be happening. So means initially what was there? The drop was there in some equilibrium state, and then we have actually keep on increasing the volume. So while we were increasing the volume, initially the contact line has remained pinned to a fixed position and its contact angle has increased. Once contact angle has received one maximum value, after that our contact line has started expanding in the radial direction and it has acquired some new equilibrium position. So what will be happening after reaching the maximum value of contact angle? Our contact line will be advancing in the outward radial direction. So that's why this maximum value of the contact angle is particularly known as advancing contact angle. Okay. And what will be happening if drop volume is further increased, the contact line will be advancing and motion of contact line. So particularly this type of motion of contact line is also called as stick slip motion. Why stick slip? Because contact line is first sticking to a any equilibrium state, and then after it has acquired the maximum contact angle, after that it is actually slipping. Motion of the droplet will not be continuous. It will be halting for some duration and then it will be moving. Okay, so that type of particular motion is actually referred to as stick slip motion. Okay. Then if we do this reverse experiment, that if we decrease the volume, so here you can see that this is the initial volume, then this dashed line is representing the reduced volume, then this dotted line is representing the further reduced volume. Okay, so in that case what will be happening, while we are decreasing the volume, there will be decrease of contact angle, and once we are having a minimal value of contact angle, after that what will be happening, drop will be receding towards inward direction. Okay, so the contact angle, minimum value of contact angle at which this receding motion will start, that particular angle is known as receding contact angle. Okay, and the difference between the advancing and the receding contact angle is particularly termed as the hysteresis range. Okay, and this hysteresis range may be very large also. Okay, so it may happen that in some case you are getting advancing contact angle is 85 degree and your receding contact angle for any surface is 65 degrees. So it may be as large as 20 degrees. Okay. So now let us try to see what happens in particularly this type of rough surfaces, why we are having that much large hysteresis. Okay. So as I have already told you that if we go for large number of experiments by different volumes, or even for a single combination also, we will be having multiple stages of minima of energy. So over here you can see one minima we are having over here, one minima we are having over here, one over here. So like that we are having multiple minimas which are existing. So these individual minimas, these nothing but represent some metastable stage of the droplet. Okay, so these local minimas, these are some local minimum energy states at which our droplet can actually be stable for some small duration. Okay, and if this droplet has to switch from one minima to another minima, it has to actually overcome some energy. So the amount of energy which one droplet has to overcome from one minima to another minima, that particular energy gap is actually, so over here you can see this is one minima and this is one minima. So the difference between these two energy states is particularly called as the energy barrier. Okay. So now whenever we are theoretically trying to determine the value of minima, so theoretically whatever the we will be finding that whatever the local minima is being obtained at the highest value of the contact angle, that particular stage is referred to as theoretical theoretical apparent advancing contact angle. Okay, so this TACA is nothing but represents the theoretical advancing contact angle. Okay, CA. And so what we are calling that whatever the local minimum stage of free energy we are finding corresponding to the highest value of the apparent contact angle, that particular value is actually corresponding to theoretical advancing contact angle. And likewise, whatever the minimum value we will be finding, that particular minimum value is referred to as theoretical receding contact angle. Okay. However, in actual practice, what will be happening while we are doing the experiments, it may happen that from the surroundings, some amount of energy fluctuations are actually supplied to the droplet. So these energy fluctuations may be because of the impact of the droplet on the solid surface while it is actually resting over the surface, or it may be because of the motion of the surrounding fluid. So there may be some residual motion into the surrounding fluid, because of which there may be some small activity or small supply of energy to this droplet. So because of that, what will be happening, there may be the situation that instead of resting over a theoretical maximum apparent contact angle, it is actually crossing some energy barrier and it is reaching to the closest next local minima. Okay, so whatever the closest next local minima we will be reaching, that particular value is referred to as practical advancing contact angle. Okay, and in similarly we are having practical receding contact angle. Okay, and then we are having one more stage over here where we will be finding that globally we are having the minimum value of the surface energy. So this particular global minima is actually the most stable state. Okay, so whatever the local minima energies we are having, these are nothing but referred to as the metastable state, because if droplet is receiving sufficient amount of energies from the surroundings in terms of some residual effects, it can move from one metastable state to another local minima state. Okay, however, once it has reached to the stage of global minima, then there will not be any change in the shape of the droplet. So because of that, it is also referred to as the most stable and the equilibrium stage of the droplet. Okay. Okay, so then we are having most stable apparent contact angle, particularly for the rough surface. So this is given by Wenzel. Now I think we are going out of time. So let us try to see these concepts in our next lecture. Okay, so I'll stop at this point.